it's time, so let me start. All right, good afternoon, everyone. Welcome to the NTUgAIP Sci-Tech Talk Series, platform where the academia and the industry come together to explore the cutting-edge intersections of science, the technologies, and then the applications in the insurance industry. And I'm Shinichi Kamiya, Associate Professor at Nanyang Technological University, and also the co-director of the Insurance Risk and Finance Research Center, which is hosting this event. And this series is a part of that collaboration between NTU and also that GAIP Global Asia Insurance Partnership in Professional Education Initiatives, where we offer programs focusing on current necessary skill set. But this talk specifically is more about forward-looking and reflect our commitment to fostering the knowledge exchange and innovation. And before introducing today's speaker, let me share a bit of logistics first. First of all, this talk is recorded and posted to the public later. And after the talk by Dr. Liu, and our colleague, Professor Joy Zhou, will moderate the Q&A session. And please use that Q&A button you should be able to find as one of the function, which allows to provide your questions. And then the moderator, Professor Joy, will consolidate and ask questions to the speakers as much as possible. And to organize that talk on time, your microphone will be muted all the time. So thank you for your understanding. So, and then all will be done by 5 p.m. All right, and let me introduce today's speaker. We are very honored to welcome Dr. Paul Liu, and Associate Professor and Assistant Chair at NTU's School of Chemistry, Chemical Engineering, and Biotechnology. And Dr. Liu earned his PhD in Chemical Engineering at the University of Cambridge, and he's a chartered engineer and a scientist. And since he joined NTU in 2018, he has focused on the decarbonization technologies, especially carbon capture, utilization, and storage. And he has published 92, probably now more than 92 high-impact papers and secured over more than 10 million research grants. And he had multiple patents as well. And he's a vice president of the Singapore Catalysis Society and leads Singapore's CCUS working group. And in today's talk, titled Carbon Capture and Storage, critical technology that helping us to move forward to net zero economy. And Dr. Liu will explain the different types of CCS technologies with real world examples. And finally, we will discuss their implication to the insurance industry. So please join me to welcome Dr. Liu. Over to you, Dr. Liu.
I thank you, Prof. Kamiya. Thank you very much for your kind introduction. So let me share my screen for the slides. And let me go to the presentation mode. So I believe you can now see the slides presented. So afternoon, everyone. My name is Paul Liu. My main research interest is to look at CO2 capture and utilization, but also CO2 capture, utilization, and storage is overall a grand scheme for decarbonization. So without further ado, let me go to the next slide. Hold on. Right, so this is a rough outline of today's talk. We are going to spend a little bit of time talking about the background of decarbonization, followed by the introduction of various CCS technologies, and a case study of an actual commercially operating CCS project. And we're going to talk about the challenges of CCS as well. So because of my technical background, I will primarily focus on financing the project itself and its technical challenges. Later on, I understand this audience is from the finance industry. So later on, I hope that Professor Zhou will help to to facilitate a discussion for questions related to the finance industry. So without further ado, the background is mainly related to decarbonization, and this presents my kind of angle of view of what is going on. So the overall, because this is related to combating global warming, so global warming with plenty of evidence is taking place. This can be characterized by the increase in the average global temperature relative to pre-industrial eras. Pre-industrial era we typically define as the year 1800. And through overwhelming scientific data, we can correlate this to the rise of sea levels and the increase of CO2 level in the atmosphere. In fact, the increase of CO2 level in the atmosphere, we can actually see a gradual increase. Even in our office buildings, we can see the CO2 are getting more concentrated and office worker getting more sleepy over the years. So the ultimate effect of the of increased concentration in CO2 is basically it affects the greenhouse gas effect of our planet. Earth is inherently a greenhouse by itself. The biggest greenhouse is in fact water vapor. Human activity has minimum impact on the water cycle, but human activity has impact on all the other types of greenhouses. So it's a very subtle balance between how much heat we trap versus how much heat we emit to the space. Increasing the concentration of CO2 is essentially offsetting this balance, and it's offsetting this balance at a quite notable speed compared to historical data. So why do we need to worry about the carbon balance? In fact, the majority of the carbon on our planet are buried underground. Because of seismic activities, these carbons are released from the rocks in the molten, beneath the Earth's crust, in the molten area of the Earth, released to the atmosphere in the form of CO2. That is what happens at the beginning of our planet. Then, because of evolution, organisms developed method to exploit the CO2 from the atmosphere to form carbon-based life forms, including plants and animals, but mainly plants. And after this process essentially take away the CO2 from the atmosphere. And then after these plants and animals die, they turn into fossil and they get buried underground. And because of this, the life forms on Earth is actually the reason the CO2 level today is much lower than prehistorical era. So what human activity is doing is to dig out these carbon again and burn them. So what we are burning is essentially the energy that plants and animals harvest from the sun buried underground, and we are basically consuming solar energy that are stored underground from millions of years ago. And this in turn offsets the carbon balance. It re-enriches the CO2 level in our atmosphere. So the consequence of global warming, in addition to the very popular picture of polar bear standing on thin ice, also include extreme weather conditions and flooding of the coastal areas, as well as the destruction of our ecosystem, including ecosystem on land, as well as marine ecosystem, especially coral reefs. Coral reefs contains microorganisms that are extremely sensitive to fluctuation of the environmental temperature. So an increase in the temperature of the coral reefs can result in mass extinction of the coral reefs, of the entire ecosystem of coral reefs, and also extreme weather conditions. So our planet's sort of weather system is is often described by chaos theory to be, extremely sensitive to small changes, also known as the butterfly effect. So small changes in temperature can often cause extreme weather conditions, and if that is translated to monetary terms, it can be translated to billions of dollars of financial losses. We know the consequence of climate change because we have actually seen them over the history of this planet. If we study Earth science, we can actually find periods of high CO2 level in our atmosphere. These are often followed by rapid fall in the CO2 level and rapid fall in the amount of animals that or the plants that was present at the time. In all previous times, climate change are caused for two reasons. One is that our Earth's seismic activities undergoes periods of high activity, a lot of volcanic eruption, followed by a relatively peaceful period. So these can cause climate change because that causes fluctuation in the CO2 level in the atmosphere. Secondly, for astronomical reasons, the Earth's orbit sometimes gets very far away from the sun, resulting in the cooling down of our planet. Sometimes it gets quite hot when the Earth, on average, gets closer to the sun. So both effects exist, and these effects are often used by so-called climate deniers as reasons to say that climate change is not caused by human. But in fact, the speed of climate change caused by geological reasons and astronomical reasons typically are 20 times slower than the rate of climate change we are seeing right now. So the speed of the climate change matters. Life can still survive during a climate change if it's slow enough. It can survive through evolution. But what we're seeing right now is a speed in which even evolution cannot catch up. And therefore, we need to combat climate change in order to preserve the existing ecosystem. The existing ecosystem is very closely related to economy. So there are several optimistic and pessimistic projection of climate change. But overall, what we can see is if we don't do anything, the Earth is going to be 4 degrees or above warmer compared to pre-industrial times. And this is a significant impact. So as of today, most of the effort argues that we need to keep the extent of global warming to within 1.5 degrees. 1.5 degree is a consequence we can't avoid today. So what can we do to sort of limit the amount of damage? And to do that, you can see all the projection requires the anthropogenic greenhouse gas emission to be suppressed to close to zero by the end of this century. So from calculations that I'm not an expert of, in general, every additional 0.5 degrees means 2.6 times more extreme hot weather, 10 times more ice-free days in the Arctic, 2.5 times the reduction in the agriculture output, 41% reduction in the overall amount of coral reefs and their associated ecosystems, and 2 times reduction in the fishery harvest as a result of damage to the ecosystem. So the more we can limit global warming, the better it is, and the more we can save the global economy. So right now, the target is trying to achieve net zero as soon as possible. The sooner we can achieve it, the more confident we are to meet this 1.5 degree target. So very often people talk about various ways we can reach that goal. In general, the consensus is there is no single solution because there is no single way. There's no single source of CO2 emission. There's no single source of. There's no single reason for global warming. Therefore, we need to tackle this problem from all fronts. So there are ongoing efforts, including circular economy. Circular economy can essentially and energy efficiency. So these efforts can essentially reduce the CO2 emission from the demand side by trying to be more efficient in terms of resource and energy use. A major effort is the development of renewable energies, and carbon capture and storage is also one of these efforts to facilitate the transition to a renewable future. Of course, there are other engineering proposals such as radiation management, such as putting highly reflective clouds in our atmosphere to enhance the reflection of solar radiation, as well as reforestation and afforestation. So these are so-called bio-based solutions to climate change. So since 2020, the global initiative or the global pledge to reach a net zero target has really taken off. So as of the end of 2024, countries that has net zero pledge covers 88% of the emission, 93% of the global GDP, and 89% of the global population. Around 44% of these economies has a pledge to reach net zero by 2050. That includes Singapore, and another 55% has a net zero pledge after 2050, but by the end of the century. So to tackle these, we basically need to also understand where are the sources of greenhouse gases. So largely, you can see the majority of the emission of greenhouse gases, primarily CO2, come from energy use. These including energy use for the buildings, for heating. Singapore is for air conditioning, energy use for moving around, and just energy use for just using electricity in general. Besides energy use, agriculture is responsible for a big chunk of greenhouse gas emission, including the keeping of livestock and the management of the manures of livestock, including basic agriculture activities, crops burning, deforestation, and the destruction of grassland, and so on. Waste management is responsible for 3.2%, so that including the methane that is emitted by landfill, by burning of the waste, by wastewater treatment, and the chemical industry is responsible for sort of the byproduct of the chemical and the cement industry are responsible for the remaining 5% of greenhouse gas emissions. So you can see the most effective way to reduce CO2 emission is to transition into renewable energies. So this is the trend of development of renewable energy capacity over the years. As you can see, we're getting more and more renewable energies, especially in these emerging areas such as wind energy and photovoltaic energy, right? But compared to the energy demand, so these are measured in millions of megawatts. Comparing this to the actual demand in energy, the rate of increase of renewable energy cannot meet the demand, even though they are growing very rapidly. Renewables still occupies or meets a small fraction of the global energy demand, which is very often tied to economic development. So the world is still dominated by coal and gas and oil. So how do we reach that goal with so much coal and oil being used? In 2020, Princeton University published the first net zero roadmap in the world, where they looked at different scenarios of reaching net zero. These different scenarios, including how we transition from a fossil fuel society to a electrified or hydrogen society. And in most of these scenarios, you can see the black line represents a linear projection of how much CO2 we can reduce. And this line aims to hit net zero by 2050. And in most of these scenarios, CCS, which represents this sort of negative triangle in most of these scenarios, will play a major role. So in all these studies, the researchers basically performed a economic optimization to see at any point in history to reach between 2020 to 2050, to reach a specific emission target. What is the optimal mix of energy supply that can achieve that targets, right? So through this calculation, what they found is in many scenarios, the optimal mix of energy supply would need to include a specific amount of energy still generated by fossil fuels, but retrofitted with CCS technology, right? So therefore, we argue that CCS will continue to play an important role, especially if we want to reach net zero by 2050. Okay, so this is my introduction. Now let's move on to introduction of CCS technology in general. So CCS stand for carbon capture and storage. So we're going to look at the capture first. The whole point of doing CCS is because we want to extract CO2 from flue gas, and we want to prepare the CO2 in close to pure form. Carbon dioxide, when compressed to 50 atmospheric pressure, becomes a liquid and becomes very easy to handle. When they're in flue gas, they are typically between 5 to 10% that are very difficult to compress. They are very expensive. So carbon capture technology is essentially a way to extract CO2 from combustion process so that we can then process the CO2. The subsequent process becomes much cheaper. So in other words, carbon capture technology is essentially a separation task. And if we think about, in secondary school, when we talk about what is needed to make a fire, we learned that to make a fire, we need air, we need fuel, and we need a source of ignition. So the result is we have a flue gas, that is the emission, including CO2, including lean air, and so on. So with this philosophy, engineers have developed a different method to achieve CO2 capture. The most conventional method is we do our burning of the fuel as per usual, except here is a typo, this should be flue gas. And before emission, we send the flue gas into a separation process to extract the CO2, and we emit a CO2-free flue gas. So then we achieve zero emission. This CO2 is further compressed and processed. So this approach is called pre-combustion capture. It's basically the separation of CO2 from the flue gas. Alternatively, we can do pre-combustion capture. In pre-combustion capture, the fuel typically consists of hydrogen and carbon, is entirely converted into hydrogen through chemical reactions. And a byproduct of it is CO2. Then all the power plant should operate with hydrogen as the fuel. In this case, the power plants themselves are emission-free, right? And we receive a stream of pure CO2, which we then can be used for storage. And in the third approach, is so-called oxy-fuel combustion, is we say we need to do CO2 capture because we want to separate CO2 from nitrogen and all the other inner component in a flue gas. So what if we just burn CO2 in pure oxygen? in this case, we just directly receive CO2 as a combustion product. We don't need to worry about post-combustion capture. So this philosophy is called oxy-fuel combustion. So right now, the most popular approach to CO2 capture is in general post-combustion capture, because this essentially is an end-of-pipe technology. We basically retrofit existing power plants, existing industrial processes with a end-of-pipe sort of treatment plants to extract the CO2 before we emit the flue gas into the atmosphere. And the majority of the commercially operating CO2 projects are related to post-combustion CO2 capture. Pre-combustion CO2 capture are very often seen retrofitted to hydrogen plants. In industry, people use a lot of hydrogen, and most of these cases, they are produced from hydrocarbon fuels through a process called reforming. Reforming essentially means that all the hydrocarbon becomes two things, hydrogen and CO2. So you need to extract the CO2 anyway, and have the pure hydrogen sold to other refineries. Therefore, this pre-combustion CO2 capture is generally suitable for the chemical industry, as well as to supply hydrogen for fuel processing. So they are quite suitable for the transportation sector as well. If we use pre-combustion CO2 capture for power generation, then this would mean we need to have an entire overhaul of the existing boilers, burners, and turbines to make them hydrogen ready. So technologically, we're not quite there yet. As of now, the burners and the power turbines, they can operate with high hydrogen concentration, but not with pure hydrogen. There are still ongoing R&D efforts to address this issue. And lastly, it's oxy-fuel combustion. So this is a relatively less studied area. Essentially, we want to combust the fuel in pure oxygen or in a mixture of oxygen and CO2. Because if you burn something in pure oxygen, the flame temperature would get too high. The flame will get too violent to properly control. So we recycle some of the captured CO2 to regulate the flame temperature. And there are a few emerging designs to retrofit existing power plants, to completely replace existing power cycles based on natural gas into one that we can use pure oxygen and recycle CO2, and to provide thermodynamic advantages. So as I mentioned before, regardless of which approach we do CO2 capture, it is essentially a gas separation task. And so we can use all kinds of gas separation technologies to achieve that, including use physical absorption method, chemical reaction, or we can use membrane technologies or distillation, right? So because of the non-technical background of the audience, I will just quickly go through these various approaches, right? So physical absorption basically means we use a porous material to trap the CO2 molecule. The potential drawback of this of physical absorption is the porous material can trap other gases. So in general, selectivity is a challenge for physics-absorption-based CO2 capture systems. And also, to trap and release CO2, we need to basically pump up to pressurize and depressurize the vessel in a cyclic manner. So the main energy usage is the pressure swings of these operation. Alternatively, we can exploit the fact that CO2 is an acidic gas. Therefore, we can use a basic material to react with the acidic gas to selectively attract CO2. Of course, other acidic gases in combustion flue gases, such as SO2 and NOx, can potentially influence the performance of the sorbent. Because now this is a chemical interaction, the majority of the energy penalty are related to the energy input to regenerate these CO2 capture sorbents. Or we can have, size selective or charge selective membranes to separate CO2 from the other component in the flue gas. So in this case, the main energy penalty are related to creating a pressure gradient for us to operate the membrane. So again, this is the source of the energy input. And also membranes are generally expensive. And when you have a membrane, once there's a hole in the membrane, it will compromise the entire membrane module. So the lifetime of the membrane module is also a source of is sort of a source of cost of CO2 separation by membrane. And lastly, we can exploit the different boiling points of different gases to do cryogenic CO2 distillation. Essentially, CO2 have a much higher boiling point or solidification temperature compared to other gas component in the flue gas. Again, the downside of cryogenic technology is quite expensive. It's commercially operating right now for air separation, but not at a scale at which we produce CO2 emissions. So again, more developments are required to scale up cryogenic technologies to make them suitable for treating industrial flue gases. So which exact gas separation technologies we choose also depends on the source of the CO2. Different sources also have different concentrations of CO2, right? So in general, we can categorize it into CO2 from power plants. Besides that, we have CO2 from the petrochem industry, and from the steel production industry. In the steel production industry, CO2 are emitted through two ways. One is we add carbon to steel, and secondly, we add limestone to form slags to make to control the quality of steel. Both processes emit CO2. And lastly, the cement industry generates huge amount of emission. So in fact, cement is the second most produced product by mankind by volume, next to clean water. So the amount of CO2 production is immense. For the cement industry, there are already ways, there are already proposals to sort of have CO2 capture built into cement manufacturing. The source of emission of CO2 from cement industry is essentially from the kilns. When you want to prepare cement, you need to produce slake lime, which is a product of roasting limestone. So limestone is decomposed into lime and CO2. So essentially have a regulated way to collect the CO2 from the calcination of limestone can make relatively cheap CO2 capture processes. Okay, so next I'm going to talk about the cost of CO2 capture. As I mentioned before, CO2 capture essentially is a gas separation process. So gas separation is the hardest separation task in the chemical industry because gas molecules mix very well with each other. They don't even separate into two different phases. So the energy required, for example, to separate 1 mole of air. So 1 mole of air is about roughly about 22.4 liters of air, requires 151 joules of energy. That's the theoretical absolute minimum. If we want to separate 1 mole of flue gas and extract CO2 from it, we need at least 300 joules of energy. And this is the theoretical minimum. In reality, to do this efficiently means to do this at a acceptable rate. The actual energy penalty is at least 2 to 3 orders of magnitude more. So all the existing gas separation technologies, when applied to CO2 capture, would result in energy consumption. These energy consumptions, when we talk about decarbonization of power plants, these energy consumptions essentially reduces the power plant outputs, right? So some of the energy could originally be used to generate electricity, and we sell the electricity. Now, these energy are used instead just to run a CO2 capture process. So we lose opportunity to sell electricity, and that is typically translated into the cost of CO2 capture or the cost of CO2 abatement. In the energy sector, they also like to say this is the incremental or the increment in the levelized cost of electricity as a result of having CO2 capture process. So right now we have the currently commercially operating CO2 capture plants are the first generation of post-combustion capture facilities. They typically cost about $100 per ton of CO2 to operate. Based on the studies, based on the feasibility or the design studies for the next generation of CO2 capture plants, because of economy of scale, because of the learning points from the first generations, some of the engineers predict that the cost of CO2 capture can be reduced to $40 to $60 per ton of CO2. The majority of these costs come from the energy cost. Okay, and lastly, we have this emerging method of CO2 capture, that is to directly extract CO2 from air. So this is a typo. The cost of directly capture CO2 from air is typically between $300 to $1,000 per ton, because CO2 concentration in air is much, much lower. So the cost of capture of gas separation becomes significantly higher. Okay, so as I mentioned, cost of CO2 capture is related to the loss opportunity to generate electricity. So how much opportunity do we lose? This is a typical example. So here are some of the power efficiencies of existing CO2 of existing power plants. For example, a diesel engine, a diesel generator is typically about 40% efficient. A gas turbine can be theoretically reaching 60% efficient, whereas coal-fired power plants, depending on how much we heat up the steam, can vary between below 40% to close to 50% efficient. So when we operate CO2 capture process, the energy penalty associated with running CO2 capture typically is of the order of 10%, right? So this is a percentage in terms of heating value, which means the efficiency of the power plant, we need to cut back by 10%, right? Cut back their efficiency based on the heating value by 10%. So 60% power plant becomes a 50% power plant. So essentially we lose 1/6 of the electricity output. So this is actually quite significant. Okay, of course, there are other sources of CO2 that are much easier to capture, including CO2 from the chemical industry. For example, the production of epoxides. The production of epoxide produce virtually 100% CO2. That is very pure. They can almost be directly sold to the off-takers. Of course, the current market has already taken advantage of these sort of low-hanging fruit for CO2 capture and supply them to the downstream industry. So the big challenge really is to address emissions with low concentrations, which are also the majority of the emissions in most economies. So besides the cost of energy, CO2 capture also has high capital costs. So this is an image of the Petronova CCS project, which is in Texas. And you can see this, so you can see at the background, this is the actual power plants. Within these power plants, there are 8 units. The CO2 capture project captures 33% of the emission from unit number 8. And this is the size of the plant. So you can see you already need a massive CO2 capture plant just to address a small fraction of the emission from this massive power station. So imagine what if we want to capture 100% of the CO2, then the actual equipment cost for building CO2 capture plant can be quite substantial. So as long as the Petronova project is concerned, its investment is around $1 billion US. And because of the cost of the CO2 of the CO2 capture process by itself, due to the low oil price in 2020, this plant actually ceased operation for 3 years, and it resumed operation in 2023. So the captured CO2 for this specific project is sent for enhanced oil recovery. This is a topic I will mention in a later slide. So this pretty much covers the introduction of CO2 capture technology. Then we're going to talk about where we're going to store it. Essentially, there are different ways we can store CO2, but most of them involve pumping it beneath the surface. And so the idea is we collect fossil fuels to generate CO2. And then we want to basically return the CO2 back into where the fossil come from. So we turn fossil fuel into fossil CO2. So therefore, there's no net sort of, there's no net movement of carbon from beneath the Earth's surface to the atmosphere. There are a few ways, there are a few proposals to do CO2 storage, including deep sea storage, enhanced oil recovery, geological storage, and CO2 mineralization. These do not necessarily, these are not mutually exclusive schemes. So first of all, we can talk about deep sea storage. The idea is when we are sufficiently deep in the ocean, the water pressure is so high that CO2 will react with water to form a solid hydrate material. So the picture on the right is a typical CO2 hydrate. This solid is actually stable when it sits on the seabed. So there has been a lot of research in the past 20 years looking at the potential risk of reactivating these CO2 hydrates, including a lot of modeling studies. And I think in the end, the conclusion is there is still a risk of especially seismic activity under the sea that could result in catastrophic reactivation of the hydrates. Then the hydrates will turn back into gaseous form and rise to the upper sea level, and that could cause, for example, rapid acidification of the ocean, damaging the ecosystem. So deep sea storage is now an abandoned scheme by mainstream research efforts. However, we can still see some deep sea storage proposals, project, and so on. But the mainstream is now we want to focus on geological storage. The whole idea of CCS originates actually from enhanced oil recovery. In conventional oil wells, we only collect between 30 to 60% of the actual oil reserve. And in order to get more oil, in order to prevent moving the entire oil production sites to somewhere else, sometimes it's more economically viable to extract more oil through so-called enhanced oil recovery. And CO2 is a useful material to achieve that, especially when CO2 is in its liquid form. It becomes very good at dissolving oil becomes almost like a organic solvent that can extract oil from the cracks of oil wells, of oil reservoirs um, to sort of double the output of the oil fields. Of course, there are also drawbacks related to enhanced oil recovery. For example, when you pump high pressure CO2 water mixture underground, the pressure underground can become quite high that you need to maintain this pressure by keep pumping. If you stop pumping, the 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 sort of the stored CO2 can ooze back out, resulting in a net loss in in carbon storage. And also, if the storage is irresponsible, CO2 can protrude to nearby underground aquifers and therefore affecting the economic activities of the surrounding areas. In fact, the underground structures are immensely complex, and very often we don't have sufficiently good idea of what is the eventual consequence of this CO2 stored underground, especially that this is a relatively new concept. So at the moment, we don't know what's the long-term consequence of storing CO2 underground. Of course, there are a lot of studies trying to assure the safety of this scheme, but at the moment, we can't confidently say everything will be very safe. So we don't have a conclusion as of now. Enhanced oil recovery is right now the only economically viable scheme for CCS. And it's particularly suitable for areas with, especially with almost depleted oil wells. These oil wells tend to don't always situate in the middle of a particular country. Sometimes they're across the border. So in general, CCS technologies would require a cross-national boundary collaboration. This can also be the case for Southeast Asia when the oil fields can be on the sea rather than, or can be offshore rather than onshore, right? So countries need to work together. So the map on the right shows a example of the Northern Lights project where the UK and Norway collaborate on CO2 project using the North Sea oil fields. Similarly, Canada and US have CO2 project on the Canadian-US border. And in this case, one of the initiative is to exploit this underground cavity across the border called around the Williston Basin to achieve CO2 capture. So later on, I will also have a in-depth introduction to this specific commercially operating CO2 project. Okay, but in terms of CO2 abatement, CO2 storage, pump CO2 underground without any oil coming back out is the only way to achieve a negative CO2 footprint. If you have CO2 coming out from underground, then actually you don't have. I mean, if you do recover oil from CCS project, you don't actually have a net emission reduction. So this is something we also need to look out for. So lastly, I want to talk about CO2 mineralization. So actually 22% of the Earth's crust are formed of minerals that can actually react with CO2 to become stable carbonates. So CO2 can be permanently stored underground. These reactions are somewhat dynamically feasible, which means they will go off by themselves. However, they are extremely slow. They are extremely slow, especially when these rocks are very crystalline rocks, right? Like this is olivine. Olivine is one of the minerals that can react with CO2. But a highly crystalline olivine itself is very stable. It will be very slow. It will take hundreds of thousands of years before it can react with CO2 completely to become limestone. So at the moment, there are efforts trying to accelerate this process, to accelerate this sort of weathering process to make it industrially, economically viable, to achieve large-scale CO2 mineralization as a way to do CO2 storage. So looking at all these steps and combining all these steps, typically capture itself is $30 to $40 per ton of CO2. Then you need to compress, you need to dry the CO2, compress into liquid form. That takes another $10 to $17. And then you need to transport CO2 by a pipeline. Typically, the pipeline is from 3 kilometers to dozens of kilometers. So that is another $2 to $10 of cost. Then it's the injection. So that's the cost of pumping the CO2 underground, followed by monitoring the capture site. So that's another 10 to 30 cents. So this adds up to roughly about $60 US per ton of CO2 captured. And this cost, if you reallocate the burden of this cost back into a power plant, this translates to about 6 US cents per kilowatt hour of electricity by a coal-fired power plants. By other kind of power plants like natural gas power plants, this cost can be different. Okay, so this is the cost of CO2. And finally, just like to share with you is an actual commercially operating CCS project. So through this website, which you will also find in the distributed slides, this website is by the Global CCS Institute. That is a Australian owned think tank. They have very comprehensive data of the various CCS projects around the world. So this map only shows currently commercially operating CCS projects. The majority of these projects are for natural gas processing, where they need to do CCS anyway. About 5 of the commercially operating projects are post-combustion CO2 projects, 3 in China, 1 in America, and 1 in Canada. So we're going to talk about the Canadian one. So the original idea is there's an oil field around this area near Weyburn. So this is between North Dakota, US, and the Saskatchewan of Canada. And to achieve enhanced oil recovery, the oil field identified 2 potential sites. One is North Dakota gasification plants. The other one is the Boundary Dam power plant, which is a coal-fired power plant that supplies the majority of the energy needs of this low population province. So capture CO2 here and here, and then the pipeline goes to the EOR sites to generate profit. This is what the plant look like relative to the power plant. So this is the power plant, and this is the CO2 capture plant, right? So some of the emissions, instead of going through the chimney, is channeled all the way to the capture plant, and for capture, processing, and for compression and sent underground. In fact, in addition to producing CO2, this system, there is a hidden sulfuric acid plant hidden inside it, because the flue gas contains, in addition to CO2, it contains sulfur as well. So sulfur is taken out of the flue gas first, and then it's recovered to produce sulfuric acid. So every day they produce 2 trucks full of concentrated sulfuric acid, and they sell this sulfuric acid also as a mean to generate additional revenue, so the overall system becomes profitable. So the rest of these are just a few of the what happens inside the power plant, and you can see the steam turbines. The output electricity is about 300 megawatt, so that's very typical of a steam turbine. of this 300 megawatt, about 60% of the electricity generated are captured and have CO2 captured. So the flue gas goes here to the CO2 capture plant. In addition to the flue gas, the CO2 capture plant also transmit cold water, hot water, as well as steam with the main power plant. So this is a typical size of a CO2 capture plant that captures about 10% of the CO2 emission from a coal-fired power plant, right? And this is what it looks like inside. A main cost of this CO2 capture process, in addition to the energy cost, is the cost of the consumption of the material used to capture CO2. This material is called amine, so it's an alkaline solution, originally designed for the sweetening of natural gases. And now, in addition to sweetening natural gas, there are proprietary formulation developed to capture CO2 as well. Unfortunately, besides CO2 and sulfur, there are all the other contaminants in a flue gas, in a combustion flue gas, right? Because fossil fuel is complex in its composition. So the flue gas is also complex in its composition. So these impurities, these contaminants will over the time destroy the CO2 capture reagents. So there are other facilities used to regenerate the CO2 capture reagent, as well as to discard irreversibly deactivated CO2 sorbents and replace it with fresh sorbents. So in the plant, you can also see massive storage tanks of backup sorbents to be replenished for this operation. So these are additional, what we call the parasitic cost of CO2 capture. So this is another another tank for storing the amines. After the CO2 is extracted in its pure form, it will be compressed to a liquid form. During the compression process, water from the flue gas will also condense out. So in addition to compressing CO2, you need to separate CO2 from water. So this is achieved through an 8-stage compression process. In a compression plant, the power consumption of the compression system itself is about, you can see it's about 14 megawatts, right? So we're capturing about 180 megawatts worth of CO2, and a few percent of this alone is used to just to do the compression. So as this, you can see the energy consumption for CO2 capture is quite high. The captured CO2 is in its liquid form is injected underground through pipeline transportation. 10% of the captured CO2 is sent to a field for CO2 storage experiments. You can see this test field is fenced. The reason is this is agricultural land, so if you don't fence it, cows will come in and start to damage the equipment, right? And this is the actual injection of the CO2 underground. So we need to monitor the pressure for the injection as well to prevent the leak. And also you can see this is what we call a metering station for the CO2 injection. So we measure how much CO2 is injected. And the effort here is that there are plenty of monitoring stations surrounding this point of injection around the area to monitor the quality of the soil and the quality of the water wells to see whether the injected CO2, which will form a massive underground reservoir, and this reservoir will gradually expand over time, whether this sort of underground expansion of CO2 storage area affect the surrounding ecosystem. So the project also have close contact with farmers in the area to see whether they have reported strange behavior, for example, to drinking water, to their animals, to their crops over time. So far so good, but this will be a century-long experiment to make sure the storage is relatively permanent. So this is what happened to 10% of the captured CO2. The other 90% of the captured CO2 is actually used to generate additional profits in the form of enhanced oil recovery. So this is on the US-Canada border when there's, it's a very flat land and you can see these oil wells, right? So these are enhanced oil recovery wells. So there are about 100 injection points. There are also about 150 points where we are collecting the sort of the extracted oil from the underground CO2. So the idea is the injection point will intermittently inject liquid CO2 and water, and to drive the CO2 water oil mixture to where there are the wells to then these wells pump out the CO2 oil water mixture. The mixture are then pumped out to a processing system where they separate CO2 oil mixture, extract the oil, and send the oil for revenue. The CO2 and the water separated will be recycled and pumped back in underground for more cycles of enhanced oil recovery. And so this is just a pipeline of these oils going to be sold elsewhere. So finally, I want to talk about the challenges of CCS technologies. Although we have successful cases, there are also many failure cases for CCS projects. For example, the Mongstad CO2 project in Norway, it is abandoned in 2013 after several billions of US dollars of expenditure. The BP also has a abandoned CO2 project because it was deemed economically unviable and the funding was withdrawn. In Mississippi, US, there was a abandoned CO2 project due to a delay, exceeded its budget and so technical issues. And of course, there are many other failure cases. So in general, we can think about a few reasons why CCS projects fail. First of all, the first wave of CCS projects, they are all first of its kind. When we develop first of its kind technologies, when we prototype these technologies, they are very often funded by the government. And government funding mechanisms are quite inflexible. They have very fixed funding and also a very strict deadline. And these are not matching well with first of its kind project, which will very often have foreseeable delays, exceeds the budget because all kinds of problems that we didn't foresee will come out when we actually execute the project due to the lack of know-how. So this is one reason these projects are often stopped because as soon as the government funding run out, there's no backup financial support. And secondly, if there's no viable business model, CO2 project can also fail. And lastly, one reason the first generation of CCS project fail is because everything is just so expensive. To build first of its kind, you often there's no existing solution, so there's a general lack of economy of scale. Of course, CCS projects are also facing various voices of skepticism. Most popular one is that people consider it to be an unnecessary distraction from developing renewable technologies. So to address that, our power system in its current form is not very well suited to renewable energies. So to maintain a stable power grid, we need a stable base load, something that renewable power, which is intermittent, cannot provide. So CCS is an excellent solution to provide this stable base load of low carbon electricity for a renewable future. And secondly, CCS technologies can be used to address emissions beyond the power sector. So even in a future when the power sector is 100% renewables, there are other emission sources that require CCS technology, such as steel manufacturing, such as the cement industry and the waste management industry. So at the moment, CCS, even CCU technologies are commercially mature. They just need to go through the learning curve, to go through the economy of scale to drive down the cost. People also consider the cost of CCS to be unbearable. But if you compare the cost of CCS in delivering low carbon electricity compared to renewables, of course, amongst all these options, nuclear is excellent. Nuclear is actually, economically speaking, the best source of low carbon electricity. But beyond nuclear, CCS, when deployed at much larger scales, are economically more competitive compared to than renewable energies. And also, this graph shows a rough sensitivity of CCS cost compared to the oil price. And this gradient essentially give us some indicative idea of how the oil price could impact the price of the carbon, right? So you can see a cost of around $60 per ton of CO2 translates to an oil price change of around $40 to $50 per barrel. This kind of change is actually well within the maximum magnitude of oil price fluctuation, right? So the impact of deploying CCS technology does not compare to the impact of the fluctuation of oil price. So in general, from a technological point of view, we consider this to be to be a cost that is reasonable to bear. Okay, so lastly, we want to emphasize that it's not a competitor against renewable energies, but instead they have their own sort of area of advantage, right? Of course, from a publicity point of view, end of pipe cleaning up technology will sound less attractive than renewable energy. You know, you install solar panels, suddenly you have clean electricity instead of having installed a massive facility just to clean up a coal-fired power plants. So from a public perspective, CCS technologies tend to sound much worse. So for the interest of time, I will stop here. I have additional chapter on CO2 utilization, but it's slightly beyond the scope of today's talk. So I still keep it there. If you're interested, you can read the slides. If you're further interested, you can write to me and for offline discussion. Okay, so thank you for your attention. I guess now we enter the Q&A session.
Yeah, thank you very much, Prof. Liu. I just want to check whether you can hear me.
Yes, I can. Yeah.
That's great. I think together with us, we have audience coming from mostly financial organizations, such as insurers, reinsurers, regulators, and also consultancy, as well as the insurance broker. Welcome to everyone. Maybe just a logistic. If you have any question, please submit the questions over the Q&A section of this Zoom, and I'm able to pick it up. But I will start first because some of the audience, when they do registration, they have put up some questions, which I will start from those first. And then we will move on to any of the live questions, if there's any. I will start from a probably more technical related question first. This relates to the interest from the audience about the risk of release of harmful CO2 during the CC2 CCS process. Just to give a little bit background, or some relevance to the insurance and financial aspects. I have seen, or we have seen, insurance products, liability protection insurance product in this space. Examples could be, paying or indemnifying the CCS facility against the environmental harmful CO2 release. At the same time, you also share about the 4 types of the storage. And the question is about how would you evaluate and mitigate the risk of the CO2 leakage over time? And what kind of the monitoring technologies are in place to ensure this is reliable, right? And if you could break down your view about how risky about the leakage over the process chain, such as the capture, the compression, the transportation, injection, which you cover in slide 40, and some of the examples in the following slides. That'd be great.
Okay, thanks for this question, Prof. Zhou. So maybe to address the risk of leakage, I can start from the upstream, that is CO2 capture. So from the CO2 capture end, CO2 in general is considered low hazard, other than it is a asphyxiant gas, so it can cause suffocation. But other than that, actually, the CO2 capture process itself, the conditions are closer to ambient conditions. The main hazard for a state-of-the-art CO2 capture plant is probably the chemical hazard of the CO2 sorbent, which is amine. So amine, first of all, is corrosive. It's alkaline. So amine leak could lead to a chemical accident. And secondly, amine, when you do CO2 capture, amine will degrade, and we need to discard of the degraded amine. These could result in unpleasant smell in the emissions of a CO2 capture plant. In terms of environmental damage, it's actually quite minimum at this stage. For CO2 compression, again, the pressure we compress the CO2 is not very high. It's up to so CO2 will liquefy at 50 bar, so that's 50 atmospheric pressure. Above it is a liquid. So when it's a liquid, a compressed liquid has quite little potential for damage. So in general, the CO2 itself during the capture phase, the risk is low. The main risk we consider are one is the CO2 sorbent. They can have chemical hazard. I guess the other one is to regenerate the CO2 sorbent, you need steam. Steam typically provided at about 200 degrees Celsius. But again, for a typical power plant, this is the coldest kind of steam. So in terms of risk, it's not significant. When we talk about CCS, we consider the main risk to be the storage site, as Prof. Zhou rightly pointed out. Especially, this is the major unknown. The capture part actually is quite mature technology. We know quite well exactly what is going on. For the storage side, this is a new idea. And here we can break it down to enhanced oil recovery and geological storage. For enhanced oil recovery, there are existing standards and practices to ensure there's no unnecessary damage to the surrounding environment. For example, if it's an oil field, there's no other agricultural activities around. So in terms of bothering your neighbor, that's not an issue. And also, enhanced oil recovery, there are oil wells serving as a point of pressure relief. So the pressure buildup of the CO2 underground will be quite limited. So that's not an issue. Then we come to underground storage. So this is the big unknown right now is what if we just forcibly squeeze CO2 underground? What is the consequence? One consequence is the CO2 can protrude to underground aquifer that is environmental hazard. CO2 by itself is very weakly acidic, so it does not cause direct harm to most living organisms. However, a sort of acute release of CO2 can sometimes suddenly increase for example, increased acidity of groundwater. So that I think is a main issue, and also acute release of CO2 could also damage the acidity of the soil in the storage area. So yeah, but at the moment, most of the monitoring are done as sort of research projects to understand what is the consequence. I guess when the technology is mature, the effort of monitoring can be significantly reduced when we have more assurance. But as of now, we still have quite intense monitoring. Quite intense meaning hundreds of observation points around, say, 5 to 10 square miles of area. So it's quite intense monitoring. I hope that addressed the question.
Thank you very much. And just a relevant question about the data, about those monitoring data, and also because those data actually helps the evaluation of the risk. Are those publicly available? And if you wanted to get this data, what is the best approach from your perspective?
So for the monitoring, unfortunately I'm not on the monitoring end. I'm more on the capture end. For the capture, I think it depends on who is operating it. So, for example, for this Canadian project, they are quite open about sharing their data. I need to look up whether they actively publish the data on the internet. But if it's government-funded project, the data should be available to the public domain. If it's commercial project, then I think it's much harder to obtain the data for monitoring.
Yeah, thanks for the insight. And just one very specific question about the risk of the CO2 release. Here's the question. Is the CCS unit powered 100% of the time? What happens if the power is lost? And would the stored carbon be released? We'd like to hear your technical engineering view.
Right. So I guess that referred to what if we stop pumping, right? I think if we stop pumping, typically we can have non-return valves to prevent the CO2 from going back up. So I don't think that is an issue. If the power is lost in the capture and in the compressor system itself, usually they are already designed in a fail-safe manner. So power outage in general will not be a major threat to CCS technology, partly because it's quite mature commercially. All the specific technologies we use are already quite mature in the chemical industry.
Sure, thank you.
Yeah.
Thanks for the insight.
So to reiterate, essentially, I mean, from my personal point of view, our main unknown, the main risk is the unknown related to the complex geological formation underground. This is something we know much less compared to the actual operation itself, which is we can control it very well.
Yeah. Thanks. Yeah. And I think, but at the same time, I think it's comforting to know that, the power disruption is actually, the risk is manageable. Right.
Yeah.
Let's
Yeah.
move to the next one. This is more about the role of insurance in the CCS project. And so the general question, our audience wanted to know, how could the insurance or insurance companies contribute to the CCS project, in many ways, right? Probably you are the scientists and engineers. So potentially you and your industry partners are the customer of or the users of the insurance company solutions, right? Especially those risk mitigation solutions. Maybe may I invite you to share about your thoughts about along this process and value chain, what are the risks do you believe it shall have the financial risk mitigation? We have talked about the liability transfer just now from the harmful CO2 release, but what about other parts of the process of value chain? You think they need to have some financial protection, but unfortunately, this is not there yet.
Okay, so as an engineer, on the value chain, I'm typically the technology provider. In fact, I have my own mini CO2 capture plant in NTU, and we are getting it insured. That kind of insurance is mainly related to the construction, the operation of machinery, of the fact that it's a very tall structure. So these are common insurance. When we move to commercial scale, what I can imagine is the party who captured the CO2 will need to have a contract selling the CO2 to a party that takes up the CO2. So maybe this is just my guess, is because I'm not, I'm just an engineer, is that maybe there can be insurance for failure to develop, for delivering a specific amount of CO2 due to, issues with operating the plant, or, oil price, these sort of things that is preventing the capturing site from delivering the CO2.
Yeah, thanks for insight. Yeah, I think I agree with you, especially for those risks related to the carbon market, which we've seen some examples, to or pilots, to cover the risk if certain promise is not met. But certainly, I think CCS it is going to be a very interesting area to look into. And further, it's probably one of the last questions on hand. This is about the CCS solution, about the greenwashing. I think one of the audience is asking, what's your view? Any part of the CCS solution is most vulnerable about greenwashing? Or have you seen any greenwashing example?
I think, well, I haven't seen specific greenwash. I mean, I've seen greenwashing example from the media. From my professional experience, I'm not very close to greenwashing, but based on my very limited knowledge of how carbon credit can be traded, I think the risk of greenwashing can be very high, because you can package some idea and it becomes a bunch of derivatives, then the original information is lost. That is very very possible to occur. And right now, CCS in general enhance oil recovery, and that has no carbon credit at all. The reason they still take place is because when we want a technology to mature, it has to be economically viable for it to scale up. So the idea is we're doing something that is not really reducing CO2, but the technology can be used when it becomes viable to have a net reduction in CO2 at the commercial scale. So it is about sort of doing the necessary evil to reach the maturity that we can have a large-scale decarbonization.
Sure.
So
Thank you.
I
Thanks
hope
for the
that
insight.
answered the question. Maybe it's not a direct answer, but that's my understanding right now. So I mean, greenwashing is I guess it's a pretty big umbrella terms. Um, it can mean very different things, right, in different contexts. But as of now, CCS, there are very small scales of actually reducing carbon footprint, but the commercially operating projects are not doing that.
Sure. Sure. Thanks for the insight. This may be the last question. This is about the funding of the project. Because insurers are also asset managers, manage a lot of money, and we wonder that the current funding you mentioned about the government, right? Who are the current funding for those commercial projects and the research project before the commercialization? And do you observe any insurers funding them at the moment?
So when a commercial stage is reached, I think the majority of the investment come from companies. For a CCS project to be commercialized, essentially, the CO2 producer need to secure a very reasonable contract that there is a buyer of CO2, and this buyer of CO2 is buying it at a price that is out of the norm. And this out of the norm price to buy the CO2 meaning it's more expensive, can be a result of government subsidy. So with these, it can be a commercial project, but very often this is the case. And so the funding come from a mixture of government funding, company investment, and government incentives for the whole. And also, the operator need to be creative at co-producing other things to generate additional profit, such as the case study I shared. The plant actually produce sulfuric acid. They sell acid to make it overall profitable. In terms of insurance participation in this space, this is not my expertise. What insurance can do. I pretty much stop at looking at the costs, not how to do clever things about the money.
Sure. I think that's probably, our colleagues and also together with the, experts in the industry probably need to figure it out. And, personally, I also hope the CCS technology is going to be more successful. For example, the IPCC, scenarios, they take account of CCS, but also mention that it is not a silver bullet. Hoping if this is successful, then the Paris Agreement, the target is more achievable. So with that, let's conclude this session. Professor Nishi, may I pass back to you for the ending?
All right. Thank you, Joy. Thank you, Professor Liu, and everybody for being a part of today's talk. I believe that we will get some, the valuable insight from Professor Liu's talk on CCS technology. And we are looking forward to seeing you at our next talk, where we continue to explore how those scientific and technological advancements are shaping the industry and also driving growth. So. And also, if you have any specific interested topics, recommendations, please feel free to drop your comments and feedback to me and Joy or colleagues at GAIP. We are more than happy to hear from you. And this is the end of today's talk. Again, thank you so much for joining us today, and have a nice evening. Bye.
Hey, thank you all.
Thank you.